Hey, I'm going to talk about transferability, but of a different model than the graph neural networks that we saw earlier. We're going to see first an invariant machine learning model on point clouds, and then we're going to see how we can generalize the transferability results that we saw earlier today and yesterday to other machine learning models that have the property that a fixed set of parameters define functions on varying size objects. And so I don't need to motivate the symmetries because we heard a lot about the symmetries in the past talk and the previous talks. But basically, we can consider two types of symmetries. The active symmetries, which are like the symmetries of physical law, and then the passive symmetries, which have to do with the fact that when you have an object, abstract or real object, and you express it mathematically, often you don't have a unique way to represent it. And so the symmetries come from the fact that you can represent it in many ways. And this is a theme that occurs in graph neural networks, but also in the parametrization of functions. There's not a unique parametrization for several functions for the same function. And those symmetries give you interesting problems. And the claim is that if we implement the symmetries, the passive symmetries and the active symmetries, you can have machine learning models and just general computational methods with much smaller sample complexity. And that has been quantified by recent work by Stephanie, and also Mircea have recent works that explain what the sampling complexity of expressing the symmetries into these machine learning models. And in particular, the symmetries that we saw of GNNs are a particular case of these passive symmetries. So in this talk, I'm going to talk about invariant functions on point clouds. And this is work with my great collaborators, including my former student Teresa, who is here. And then we're going to talk about a theoretical framework for this transferability of machine learning models on varying size objects. And this is related to, well, it's kind of like what Eugene presented yesterday. And also, if we have time at the end, I can tell you a little bit how we can use these ideas to also other space, like PDE solvers, that you can think of like any-dimensional in certain ways. So there's a lot of work in machine learning on point clouds, including work by people in the audience. Nadav and Pablo have worked on machine learning on point clouds. And there are many applications. In particular, in our case, we were motivated by talks with our collaborators in astrophysics and cosmology, where they had these problems that were basically regressions on point clouds. They had like very expensive hydrodynamic simulation, and they wanted to predict some properties of these point clouds from cheaper simulations that they got just from dark matter simulations. And then basically it was just like a simple regression on point clouds that were invariant with respect to permutations of the points as well as rotations of the point clouds. So we wanted to have a machine learning model for that problem. So mathematically, you can write it as here, like here your point cloud is n points in RD. And then we have the action of the orthogonal group on the left and of the permutation group on the right. And we want to write the functions that are invariant with respect to that. So in order to tackle this problem, first we can look at the action of the orthogonal group on the left. And this is a problem that has been studied for a long time. And there is very classical mathematical tools to address it. The first fundamental theorem for invariant theory tells you that a function of n points in Rd is OD invariant if and only if you can write it as a function of the gram matrix, of the inner products of your points. And this is something that was also mentioned in the talk by Risi on the first day. So basically, you take your points, you construct these invariants, which are the inner products, and then you can apply any function to the inner products, and that's going to be invariant. And you can use that to construct equivariant functions as well, but here we're only interested in the invariance. So you can write, mathematically, you can write it as there is a diagram that commutes. So any function that is invariant, you can write it as a function of the inner products first, and then the application of a function on the inner product space. And now we're going to work with the permutations. So we know that now the function was OD invariant if and only if it's a function of the Gram matrix. So if we apply a permutation to my points, then on the Gram matrix, it ends up being the action of permutation by conjugation on the Gram matrix and multiplied by the permutation on the right, and then the transpose of the permutation on the left. And then I get the symmetries of the graph neural networks. So the permutation of rows and columns on the adjacency matrix corresponding to this Gram matrix. But we're not going to use GNNs. We're going to use invariant theory. And the reason why we don't want to use GNNs is because constructing the graph is order of n squared. And we're going to use some tricks to not have to construct these O of n squared features, because in this cosmology point clouds, the n squared is too large. So we're going to just do O of n times d complexity, with n is the number of points and d is the dimension of this space. And we are going to use interesting mathematical tools that maybe we can use more broadly. We'll see. I mean, I don't know. We just use it here, but maybe these ideas could be used in other problems that you're interested in. So the idea is the following. So we have these symmetric matrices that we're acting by permutations, by permuting rows and columns. And then we're going to see this group of permutations inside a much larger group, which is a group that permutes the diagonal to a diagonal and an off-diagonal to an off-diagonal. So we know that if we are acting by permutation of rows and columns, we do that. But not every permutation that permutes a diagonal element to a diagonal element and an off-diagonal element to an off-diagonal element comes from a conjugation. Right. So then we have a larger group. But if we think of this action, this is a much simpler action to analyze, because we can construct the invariants. Just it would be like the set, kind of like the set of the diagonals and the sets of the off-diagonals independently. And so for these ones, for these sets, we can use the elementary symmetric polynomials to characterize this, or we can just think of using deep sets on these objects. So if the group is much larger, then the set of invariants is much smaller. There's like the inclusion goes in the other direction. And this is what Galois theory tells you. So in Galois theory tells you that if we can construct a set of invariants that are only fixed by the desired group, which is the smaller group, and then no other bigger group fixes all these invariants, then those invariants are going to generate the field of invariant functions for the smaller group, which is what we want. And then there is another theorem that tells you that if we can generate the field of invariant functions, so meaning that every invariant function can be written as not just sums and products, but also quotients of these invariants, so as generated as a field, then there is a unique bad set. Sorry, there is a bad set which is closed and measures 0, which is the set of orbits that you cannot distinguish with this approach, because we know that we cannot expect to distinguish every possible orbits by the action of permutation by conjugation using n times d variants, because we know that we cannot solve the graph isomorphism problem like that. OK, so how do we do that? So we consider a sequence of inclusions of groups, and then for each group, you can consider the field of invariant functions for that group, and then the inclusion goes in the other direction, right? So here we have for the identity, we just consider the field of rational functions on all the entries of the matrix. And then for the group that permutes diagonals to diagonals and off diagonals to off diagonals, we can consider the field of functions generated by the sets of the diagonals and the sets of the off diagonals independently. Yes?
extensions of the symmetries? Or?
Yeah, so this is field extension. Yeah, these are field extensions, and then this extension is Galois. So since this extension is Galois, then you can see that the invariants, the field of invariant functions with respect to the middle group can be constructed by adding an extra polynomial. And this extra polynomial, we can write it down, and it's going to be a polynomial that is like the sum over the entries of the ij from 1 to n of xii, the diagonal element, times xij, the off-diagonal element corresponding to that. And so what we can prove is that the sets of the diagonals, the sets of the off-diagonals, and this extra object generate the field of invariant functions for the action that we care about. And that's what we do. And so with that, like algebraic result, then we can construct a machine learning model. And then we're going to use deep sets to construct the machine learning model instead of just using the symmetric polynomials. And the reason why we don't want to use the symmetric polynomials is because the symmetric polynomials are polynomials in n square variable, or n choose 2, if you're considering symmetric matrices. So the symmetric polynomials depend on the number of variables. You cannot evaluate a polynomial in more variables than the variables that the polynomial has. But if you translate into a deep sets architecture, then you get a machine learning model that can be evaluated in any size point cloud, and that's what we want. And so we use a result by Yusu Wang and her postdoc that tells you that actually you can have a universally approximating deep set by going to dimension of the intermediate space to be like 2 times k times n, where k is the dimension of the space and n is the number of points. And in order to get the universality result in our paper, which is that basically says that you can, using this architecture, which is like the deep set of the diagonals, the deep sets of the off-diagonals, and the extra guy that we got from invariant theory, with this architecture, using these deep sets with this specific property, you can universally approximate invariant functions on symmetric matrices outside an invariant closed measure 0 bad set. Yeah. And then, so this architecture is not that useful because it requires you to use n square objects, and I promised you beforehand that we're going to use n times d. Otherwise, you might as well use a GNN. And so what we use to do a dimensionality reduction here is we use the fact that you can do matrix completion if you have like a rank D matrix. The matrix of inner products is rank D. So if you observe D rows of this matrix, then you can reconstruct the entire matrix. So using like ideas from low rank matrix completion, then you can write a deep sets architecture that only uses like a piece of the matrix. But we have to do something extra, which is when you choose the rows of the matrix, you kind of need to be able to do it in a way that keeps track of the symmetry. Otherwise, you lose the symmetry that you had before. So in order to do that, we do a construction where, given our point cloud, we construct D centers, which can be constructed in an equivariant way. So for instance, you can take the like k means for k equals to D. And these D centers need to be equivariant, and they need to be invariant with respect to permutations. So for example, you take these centers ordered by norm, and then you construct this like augmented matrix. You take this matrix of inner products, and then you can use like this part or that part to write the deep sets model that is going to give you something invariant. So basically, the way it works is your machine learning model is going to be a deep set of the inner products of your points with the centers and the inner products of the centers with themselves. And this architecture is going to be universally approximating outside an invariant closed zero-measure bad set. And that is the model that we have. Any questions or comments so far? Yes?
I didn't follow exactly how this whole Galois business and the F star you added, so what that gives you exactly, theoretically?
So what the F star that you added gives you to be able to tie the permutation of the off diagonals with the permutation of the diagonals so that they are consistent with permuting rows and columns.
So it's to pin down the larger group to the smaller symmetry. So the group that will actually care is just Sn acting by permuting rows and columns together. But we first consider a larger group of separately permuting the diagonal and off-diagonal elements.
Yes?
So, do you know something about this, like more about the structure of the bed set?
Yeah, the bad set is, it comes from the zeros of this polynomial F star. Yeah. Well, not just the F star, but the zeros of all these polynomials that you have as generators. Because basically you're saying these polynomials that I have are field generators. So every function can be written as products and sums and quotients of functions of this form. So when you have them in the denominator and they're equal to 0, then that's where you're not able to separate orbits.
So if your input would be like an adjacency matrix, what would this give us?
What do you mean what this gives us?
I mean, like you're computing something that is invariant over graphs.
Yeah.
So what is the semantics of? I don't know what you.
It would be exactly the same computation that we have before,
Yes,
right?
I know,
Yeah.
But like, there must be like a more precise meaning.
I don't know what is the more precise meaning, but I'd be interested to know,
Okay.
like semantically, yeah.
Do you mean that you specialize the entries to 0, 1 when you say adjacency, like just binary?
Yeah.
So then, for example, the F star will simplify a little bit, right? Because the F star, so that you can
Sorry.
flush the
sorry.
definition of F star. If we only have a adjacency matrix that xii, xij are
That's
binary,
gonna sum to.
yeah. So then, let's say if you have a hollow graph, then actually F star would be 0, which is pretty bad.
But that's for symmetric. Yeah, that's for undirected graph.
Sorry.
If you would have a directed graph, it would.
Directed graph.
Then you would again have like a little bit more.
Yeah, that would be different. Like in general, this works for any weighted
Sure.
graph.
Yeah, no, I know. Yeah.
Yeah, I think this is less powerful than WL than I think for matrices, right? Yeah, so yeah, but you get it from a different technique. Maybe there's a way to make it. So actually, this choice of F star we came up with, but then we actually were able to prove that random invariants, like if you add a random invariant here, that also is with high probability a field generator for the thing that you want. So maybe you can just have some random invariants if you can construct invariants, and that would give you something that is more expressive. And it would give you invariants that may be useful for machine learning. Yeah. So, Yusu, yeah.
So can you just go to the previous slide? So the concentric, so for example, from Hopkins, and in order to buy 2 norms, would that be not stable potentially?
Yeah.
Would that be an issue?
Yeah, that's not stable. There are other invariants, the other polynomial invariants that we can construct that are not like k-means, because k-means can be discontinuous. But they are like degree D, so I don't know. We have other possibilities. We thought k-means because it's easy to explain, but yeah, that's true. Actually, any centers that have this property would satisfy, would work for the theorem. Yeah. Great. So we have some numerical experiments showing that it works okay, right? I would say that's the assessment. It could work. Yeah, I think it's interesting. So now I'm gonna take a step on a different direction but related, and we're trying to do transferability of machine learning models that, as like graph neural networks and machine learning models and point clouds and deep sets, have the property that you have a fixed set of parameters, and that defines a model for any possible input size, which I think is what we want in these spaces. So the question is, when you make a model that has this property, that you can evaluate it in different size objects, you're making some assumptions, and we kind of wanted to understand what are the assumptions that we're making when we do that. And so, for instance, one example is this the GNN transferability that we heard a lot about. We have a sequence of graphs that converge to a graphon. And then the GNN, which is, you can think of it as a set of weights, define functions for each of these possible size graphs. And then transferability is basically just continuity. I think that was said earlier today. Basically, if you have that a sequence of graph converges to a graphon, and then you have that your model is continuous, so the evaluation of your model, Fn converges to the F infinity, which is the evaluation of the model corresponding to the graphon. Then if you have that, then you can have some size generalization results, which is that the evaluation of the model and size of graph n minus the size of graph n converges to 0. So, and there's a lot of work on that. So mathematically, what do we have? One way of thinking about it is that we have a sequence of input sizes, vector spaces where you have your inputs. And maybe in each of these vector spaces, we have a group acting. So for instance, in the GNNs, we have the group of permutations acting by conjugation. And in deep sets, we have the group of permutations. Maybe you don't have a group, but in these examples, we do. And then we have a machine learning model given by a fixed set of parameters that define a class of functions for each of these vector spaces. And then we have a limit space, and then also these parameters define a function in the limit. So one way to think about it is that we can think of these inputs of size n inside the inputs of size n plus 1, inside the inputs of size n plus 2. So maybe we have an embedding of these spaces. These phis are just embeddings. And then something that we may want to have is that applying the model and then the embedding is the same as applying the embedding and then the model. Well, we also need embedding for the output spaces, but that's what we're saying. So the compatibility condition is that the diagram is basically asking that the diagram commutes. Applying the embedding and then the model is the same as applying the model and then the embedding. And then these embeddings need to not just be like any embedding, but we need to be an isometric embedding, so it preserves the norm. And we can identify a size of a graph of size n inside maybe a graph of size n plus 1 or a graph of size 2n. And then we have the limit space, which is going to be the direct limit of these finite dimensional spaces. So or maybe you can think of it as the union of these n-dimensional spaces quotiented by by this identification. We may also quotient by the identification coming from the group, but we don't have to. And then the transferability is just the continuity that we have when the sequence of fn's converges to this f infinity defined in the limit, and this is a continuous limit. And so the choice of topology that we give to each space, to all these spaces, is going to be important, because it's going to give you what the continuity is, what it means to be continuous. And so I have a few examples. So how do we embed a small object into a larger dimension space? So for instance, for sets, there are two natural ways to do it. The zero padding, which is like just adding 0 or no for the next entry of your set, or the duplication. So say the set of 1, 2, 3 is the same as the set of 1, 2, 3, 1, 2, 3. Well, they're multi-sets, but yeah. And so then we can think, what is the norm that make that embedding isometric? Not every norm make this embedding isometric. And so you can think of, for these norms that make this embedding isometric, what is the metric in the limit space? So for instance, if we look at the zero padding, we get infinite sequences with the LP metric in the limit. But if we look at the duplication embedding, then we get probability measures with the Wasserstein p distance. And so basically, and this is what Eugene explained yesterday, different choices of normalizations of your models are compatible with different norms and are transferable with respect to different limits. And so what you can do is think about how your model, your data, and your topology align. So you need that. So for instance, deep sets is compatible and transferable for the zero padding and the one norm, but it's not going to be compatible for the duplication and the p-norm, deep sets without normalization. It's not going to be compatible for duplication with the p-norm or with the infinity norm. But if we do deep sets with normalized by n, divided by n, then that's not going to be compatible for the zero padding, but it's going to be compatible with the duplication and the p-norm. And it's going to be compatible and transferable. So depending how you think, like you think about your graphs, how are my graphs growing? And so that would tell you what is the right topology that you need to put in the spaces, and what is the right limit that you have to think about. Yes? It can be relaxed. Yeah, in our paper we consider isometric embeddings, but we believe it can be relaxed. And also, this is kind of like a strong assumptions setting. You could have less assumptions, and you can still have transferability. This is just a set of assumptions that maybe not necessary to have it, but that's just one way to think about it. And maybe something that I should have mentioned before, and I forgot, is that this construction is related to representation stability that tells you that if you have a sequence of representations of the symmetric group, for instance, then the dimension of the linear maps of these representations stabilizes up to a certain n. So mainly like that you can write all these linear maps with a finite set of parameters. So for instance, that is something that appeared not with those words, but appears in the IGM paper of Hagai, where you have these invariant graph networks on K tensors can be written like the dimension of the space is a function of K, but not a function of N. And this is like a consequence of that. Like you can write all these linear maps that are equivariant with a finite set of parameters. So if you don't have the action, you still can do this, but you may not have the same expressivity that you have if you have the action. Like at least you have like this full expressivity for linear maps. And there's another paper by Levin and Diaz that does this construction of these any-dimensional networks for to find the right basis, so that you can find the right basis so that all these diagrams commute with an algorithm. Yeah. Okay. Is this drawing table clear? Like, what is the idea of what's going on here? Just that we're asking how is the data growing, and what is the normalization that I need to give to my any dimensional model, or any dimensional model, so that it is compatible and continuous with respect to that way of growing the data. So basically, like, we have this here, we have this map that tells you, like, given a set of parameters, how you define these fn's. And so, there's not a unique choice. You can have some scaling with n. So for instance, in the talk by Samuel yesterday, he had a scaling in the data that depended on n. But here we have a scaling in the model that depends on n. So I don't know if we can use that in this framework or not. Okay, so what can we do with this? With this like abstract kind of nonsense framework. So we can modify existing architectures to make sure that they are transferable for a given consistent sequence and a given task. So for instance, we can look at the IGNs and see how to scale them so that they're consistent for graphons or that they are consistent for zero padding or something. GNNs, machine learning models on point clouds, etc. We can ask how do we make them to be transferable. And then the task needs to be expressible, as Eugene mentioned yesterday, and needs to be continuous for all data sizes. And so there is kind of like some form of alignment between the task, the topology, and the model that we need to have in order to have transferability. And we can recover the generalization results that we saw earlier this morning for this framework. And so this is a bound that Antonis presented this morning from the Zhu and Manor paper that has been used by him and other groups to produce generalization results for GNNs. And the same thing will apply here. And something interesting that you can have here is you can consider distances between finite objects and infinite objects, because you can see everything in the infinite space. So actually, you can have like this out of distribution. You don't need a sequence of objects that converts to the exact distribution that you have, because you can think of your finite distribution and your infinite distribution in the same space. So you can have kind of like a out of distribution bound that depends on like the distance between the measure, finite measure, and infinite measure, which we didn't see in his talk, but it's more or less the same. Okay, so that's the generalization result. And then we have some numerical illustrations of what's going on here. So for instance, so in this example that we have in the top, we look at compatibility or non-compatibility and transferability or non-transferability of GNNs and we just have like random weights GNN, and then we look at the evaluation on different sizes of objects. So it's just like a synthetic example to see how this behaves with different objects. So then if we have something that is transferable, when the number of when the size of the graph goes to infinity, then this concentrates and then it converges to the value of the expected value of the model, right? Because it's just like it's like some random weights that define functions on objects of different size. And so if you have like it converges to something in the limit, a model in the limit. But then if you have something that is incompatible, then you cannot have, like if you evaluated the different sizes of n's, and you think about what is the limit at the different values of n's, then you don't get a straight curve just because it's not well defined, because it's not compatible. So the diagram doesn't commute, so looking at the object in the limit is not even well defined, so that's why we get this curve here. And then it's like, and then compatible but not transferable, like the object in the limit exists, but you can convert to something that is not the object in the limit. And then you can also have some numerics explaining the alignment of the model and the task, and you can consider tasks that are continuous or not continuous with respect to the topology of the limit, and then you have the ones that are continuous are going to have smaller error than the ones that are discontinuous. And this is what we do here. This is for point clouds. This is for GNNs, and this is for deep sets. Yeah. And so, for instance, so for the point clouds, if the target here is the distance of a set of points, the minimum distance to the origin, so that's continuous, say, with respect to the Hausdorff distance. And so the best performing model is the point nets. But if you take another task, which is the average of some statistic of your data, then the best model is going to be a normalized deep set. Yeah, this is what these examples show. So to finalize the talk, any questions so far? Yes?
Do you know anything more about conversion states? Like
Well, what we know is this generalization result. So you're asking, how does this depend on n? For n, no, we don't know. Yeah. Yeah. So I guess that what you would do is you would use the techniques that were shown earlier today that depend on the model, like the convergence of the model that were based on being able to compute the BC dimension of the class of GNNs and so on. I think that maybe would give you that, but I'm not sure.
So would that show up in the W1 system?
Sure, yeah, but this term would be 0 if you have, like, say, in the graphon case where like you're sampling from. Well, I don't want to claim that. I don't know. Yeah. Okay. So finally, I would just tell you like how this like coordinate-free, how this dimension-free idea could apply to a different setting that is completely different than what we were talking about before. So I'm going to consider a PDE identification problem. So I'm going to have some data generated by a PDE, and then I want to learn the equation that this PDE satisfies in a way that is coordinate-free and dimension-free. And then I'm going to use that parameterization to parameterize a class of PDEs that can be given in any dimensional space or in any manifold. So for example, the way I would do it to make it coordinate-free is I'm going to use the differential forms to parameterize, to express the PDE. And that is coordinate-free by definition. And then also, in some cases, you can think about them being dimension-free. So for instance, if I have the heat equation, I can write it as du dt is equal to the Laplacian of u, or I can write it as du dt equals to the Laplacian of u using this formulation that is independent of the coordinate system of my manifold. So then, simple example, say that I have a PDE that is given by a coupled scalar fields. What I can do is, and then my function say that it's an orthogonally symmetric second order PDE, and I want to learn this from data. So then I can say, well, my function is going to be a function of my fields, the Laplacian of my fields, and the inner products of the gradients of my fields. That gives me kind of like a basis that is independent of the dimension of the space. So it's just like an any-dimensional framework. And so if I can write the PDE as a function of these objects that are defined for any space, then that would give me a parametrization for this PDE in any possible domain. So then we have this basis. We express kind of like we use this as a dictionary. We learn functions of these dictionary elements. So we express it as a function of these dictionary elements. And then we can evaluate this function in any possible space. So it's kind of like an example of another any-dimensional thing that is not GNNs, point clouds, or sets. And then you can do that. You can do the PDE identification in dimension 1, and then learn a function of my dimension 1 basis, and then just replace these dimension 1 objects by the corresponding objects from the other domain that I change. And then I use the same kind of like neural network prediction, like the same function for these other basis elements, and I get something that is consistent in a different space. And you can do that for other systems. And then I guess the question would be the same as we had before. What assumption are we making where we are learning these PDEs in any manifold, in any dimensional space? Like, can we have this analogous transferability properties and understand what is the model assumption that we going from one dimension to another dimension? Kind of like another example. I don't have the answer to that. I'm working on that. This is just like to give another example of a space where this theory can apply. So to finalize, I would say that we talked about invariant functions on point clouds via these invariant features. We saw that Galois theory delivers this genetic universality. We use tricks from low-rank matrix completion and deep sets to give this information theoretically optimal complexity models. And then we looked at this theoretical framework for machine learning models on varying size objects. In order to do that, we need to make the assumption of like how these objects grow in size, look at these consistent sequences, and we looked at the conditions that we needed here were like compatibility and transferability, and we can have a hypothesis for aligning tasks, topology, and models, and then we saw that one possible application is PDEs. That's it. Thank you. And I finished early. Yes.
Yeah, thanks for the nice talk. I have a question about the last PDE application. So did I understand correctly that you want to discover the differential equation from data?
Yeah.
So how does this compare to PySyndy, for instance? So these methods where your dictionary is just, your x, your t, your first derivative of x with respect to t, and so forth, and then you just kind of fit a lasso. Yeah.
So it's the same idea, but the way you express your basis is in a way that is independent of the underlying manifold, which Syndy does not. So you have these ways to express your basis that allows you to change the basis elements and keep the coefficients or keep the functions of the basis elements and apply it to other space. So you could do SIMD, but instead of using the first derivative and the second derivative and whatnot, you use it. You write it as a function of the manifold, so that if you change the manifold, you still keep the coefficients and you get an analogous PDE on a different space. Does that answer your question?
Yeah, maybe we can just maybe ask later a bit more.
Other questions?
So still about the PDE, another thing that reminds me, I already know is different, right? But so I think people doing these neural representations have some claim of not of changing the dimension, but to be independent of something like the cardinality of the data or something like that. I don't know if that compares in any way. So in a sense, maybe the question could be is if there is a version of the method you have that works at in a using spectral coordinates.
Yes. So something that we can do is so the example that I gave here is like a time evolution PDE. But if you have something that is not time evolution, like say the Laplacian equals to a function, then you write this. You have to do some form of manifold learning in order to express the PDE. Where if you have this time evolution, then the manifold coordinates are kind of like already given to you by this. But you can say, well, then you have an implicit function, like you construct these objects, and then you say, there's an implicit function of these objects that I need to learn in order to have the PDE. So I construct these objects for many possible initializations, and then I learn the PDE as a manifold in these coordinates. So I think that relates to what you said. But I don't know much more about that. Yes.
Yes, so I'm interested. Thank you for the talk. I'm very interested in the part where you have alignment between your task, your model, and your topology. So I understand that if you're using different norms and then you have the different topologies and you can align the model with that. But can you speak a bit more on how you define task alignment with either the model or the norm? Is it just Lipschitz continuity, or you have other?
Lipschitz continuity is a necessary condition for the thing that we have to work. I believe, at least locally Lipschitz. So the task needs to be continuous, or Lipschitz continuous at the limit. And then it's not just the task, but also how your objects grow. So in this framework, the objects need to grow according to a consistent sequence that is compatible and continuous. Yeah. Yes.
For the invariant functions, does it generalize to semigroups?
I don't know. Do you have a Galois theory for that?
No, I don't know. I'm asking you. No, because, for example, with the Weisfeier-Liemann, you have these doubly stochastic matrices. If there is no inverse, they form like a semigroup. And I don't know whether there's any way to get some invariant functions. Whether there are generators. I don't know. I don't know enough about this.
I don't know.
Yeah.
Yes.
Yeah. So regarding the first part, so you use a certain amount of invariance for what you can prove, You try maybe to use less invariance, more invariance. I mean, you use 3, right? But
Yeah, we can. Yeah, we only use 3 for this here, but there's some other students that are looking into adding more invariants, because when you add more invariants, the size of the bad set, the bad set gets smaller. So you can get more expressivity by just adding more invariants.
But that might go into the rabbit hole that Hagai presented the first day on the bootcamp, that you were doing explicit feature engineering. So,
Or you could do random ones.
yeah, so maybe random ones would be more interesting.
Okay.
No other questions? Let's thank the speaker.
Thank you.